I want to take a look at a number of discrete impulse responses and then see what their according function I get for a step response. Now remember, an impulse response would just be a single or step response first. It'd be is an input and then is all zeros and then becomes one everywhere. Where an impulse response, remember, is just all zeros, a single one, and then zeros the rest of the way. So we want to take a look at what does things look like given an impulse response, because it's the classic way we like to characterize linear systems. And then see what does the step response look like, and really kind of not only as an exercise of understanding the approach, but it also is a really good sense of getting intuition of what's going to happen through these kinds of convolutions. And so you begin with the first one. You say, well, imagine I just put this into a boxcar filter. This is a very well-known structure. And one way to approach it is to take the h1 of z as this classic sort of ratio of things. Another way to talk about it is I just got the four pieces there, each of them with their single delay. And it's not clear which way I'd rather go. It is clear that if I do a step response, that its transfer function is a 1 over z to the minus 1. So if I look at its y1, it's going to be 1 minus z to the minus 4 over 1 minus z to the minus 1 squared. That's going to get a little more interesting. So you're thinking that's a really neat formulation. Is that the easiest way to get the solution? May not entirely be. And in fact, it might just be easier to say, I've got an impulse response, then times a step response, which that delta n becomes a u of n, delta n minus 1 becomes a u to the n minus 1, and all the way to the u to the n minus 3. This probably becomes a bit easier to plot and easier to think about because I'm going to start off with all zeros. Then I get the first one, which is be 1, then 2, then 3, then 4. And at 4, it just stays at 4 pretty much till the age of the universe. And we're done. And that works out in a fairly easy way to look at this. Now, imagine I take this h of n, this impulse response, and just make it a little bit more interesting. Maybe I make it now be sort of 1, but then it decreases linearly down. Well, how would that sort of change this conversation? Well, now I could actually get a z transform out of this. I get all of the z's out of minus 1, minus 2, minus 3. And then I could convert that, and start doing other kinds of transformations. Or I could just realize, you know what, if I take the h of n, the same thing I did here, and then look at it as a step response, it's going to give me a step of u of n, u to the n minus 1, n minus 2, and n minus 3. So here's what's interesting, right? It then just becomes a step 1, then add 0.75, then add a half, then add 1, and I just go flat. Okay, and I go flat pretty much at that particular value at 2.5. Great, right? Okay, so that works out in a pretty straightforward way. Now, there are times I will want to do this analytically to make a little more sense of what's happening here. So let's look at this third one, where now it's 0.5 n to the minus 2, u to the n minus 2. So basically, it's a sort of classic case of 1 and then dropping down by half all the way down, but I shifted it by 2. Okay. Well, the first thing I'm going to expect on the y is that it's going to get shifted by 2, and then I'm going to see something converge. Okay, that's great. That helps me quite a bit in getting this in a good place. So then I start off and say, well, okay, from this structure, I know what my z transform of this is. It's going to be z to minus 2, and then I get a 1 minus 0.5 to z minus 1. Okay, great. This also then says, well, given this, I could then say, well, how would I then approach solving it? Well, the output is then going to be z to the minus 2 over this factor and this factor. Well, now I get a nice partial fraction decomposition. But once I do it, what I find is I get 2 times 1 minus to the 0.5 to the n minus 2 u to the n minus 2, which means it starts off with 0 all the way till I get to 2. And then I'll eventually, as n gets large, right, this term eventually goes to 0. Any term less than 1 as I go to infinity goes to 0. And I keep taking successive powers of it. And so therefore, I know it's going to go to 0. So eventually the top is 2. And then I have this transition up, which starts at 2, then 2 or 1, and then 1.5, and on my way up. Okay, great, right? And I get a similar sort of case if I take one where it's say 0.6 and then drops. Similar sort of h of z that I would get out of there, but now it's minus 0.6. Similar sort of z transform, similar sort of solution by sort of pulling out the parts. But now I get a peak where it's 2.5 and goes all the way through here. Interestingly enough, if I were to look at this from its frequency response, in case you're curious, the frequency response of this at omega hat equal to 0 was 2.5. And the frequency response at h at omega equals 0 is 2. So everything here is consistent. Everything kind of agrees, but it's interesting to kind of get different pieces and ways to look at each of these responses and get really comfortable with all of the intuition with all the parts.